today we'll be doing enzymes and their regulations. So properties of enzymes. What are the properties of enzymes? So enzymes are biological catalysts. Enzymes are biological catalysts. They accelerate chemical reactions. Whatever chemical reaction is happening, they accelerate it without being consumed in the process. So they are not being consumed in the process. Okay. Enzyme increases reaction rate by lowering the activation energy. Whatever the activation rate was, they lower the activation energy rather than altering the overall free energy change delta G of the reaction. They achieve this by stabilizing the transition state. How do they do this? They stabilize the transition state by bringing substrate into proximity. They bring the substrate into proximity and properly orienting reactive groups. Okay. Importantly, enzymes do not change the equilibrium constant of the reaction. They only help systems reach equilibrium faster. They do not change the equilibrium of the reaction. They just let the system reach the equilibrium faster. Okay. Number 2, extraordinary catalytic efficiency. They have extraordinary catalytic efficiency. They exhibit remarkable catalytic power, often enhancing reaction rates by the factor of 10 raised to power 6 to 10 raised to power 17 times compared to the uncatalyzed reaction. Think how fast it occurs. Like 3 into 10 raised to power, let it be. For instance, enzymes such as carbonic anhydrase can process millions of substrate molecule per second. 1 second, million. This efficiency arises from several catalytic strategies. कैसे होता है? How does this occur? Number 1, acid-base catalysis. Number 2, covalent catalysis. Number 3, metal-ion catalysis. Number 4, proximity and orientation effects. So next is the concept of turnover number, kcat. Reflects how many substrate molecules of an enzyme converts per unit time when fully saturated. When the solution is fully saturated, how many molecules of substrate is substrate molecules an enzyme converts per unit time. Okay, kcat. This is kcat. Next, kcat or turnover number. How much turnover occurred in a period of time? You can ask, like in business, how much turnover occurred in a year. The time frame is taken and how much income was generated, it is asked. So number of molecules in a period of time per unit time when it was fully saturated, and this is converted under the influence of an enzyme. So that's what we are seeing, kcat or turnover number. Number 3, specificity of enzymes. Enzymes have specificity. Let us see this. Enzyme specificity, bond specificity, group specificity, substrate specificity, optical specificity, geometrical specificity, and cofactor specificity. So there are some. So let us think A and B. So they have a bond specificity. Okay, we'll see the group specificity of them. Okay, we'll see the substrate specificity, if this substrate is even like bondable to the enzyme, right? It is bondable to this but not this. Next is optical specificity. If this optical geometry is like working in favor to the enzyme geometrical specificity and cofactor specificity. Let us see. There are two types of mechanism of substrate interaction. One is lock and key model, another is induced fit model. So what happens in lock and key model? The enzyme and substrate are taken, and they are corresponding to each other in shape. Okay, so they are complementary to each other, so they fit tightly with each other easily. But in induced fit model, we see the substrate and enzyme are not complementary to each other, but the enzyme induces and converts itself into a to be complementary to the substrate. Okay, that's what we are seeing here. Next is one of the most defining properties of enzyme is their high specificity. This specificity can be absolute specificity. Enzymes act on a single substrate. Okay, group specificity acts on substrate with similar functional groups. Stereo specificity distinguish between optical isomers D versus L form. Okay, absolute only one substrate. Group specificity with similar functional groups. Number 3, stereo specificity distinguishes between optical isomers. Okay, the lock and key model given by Emil Fischer initially explained specificity, but modern understanding favors the induced fit model, Koshland. Okay, given by Koshland, where enzyme structure adjusts upon the substrate binding to achieve optimal interaction. Next is saturation kinetics, Michaelis-Menten behavior. So what is happening? We see substrate concentration on the x-axis and reaction rate on the y-axis. So this curves go like this: concentration of substrate versus reaction rate. Okay, so at Vmax by 2, what is Vmax? The maximum velocity this can reach. Okay, this can reach like this, Vmax. But what at the half of Vmax, we see when we correspond this to the concentration of substrate, we get a Km. Okay, next we are seeing when enzyme inhibition is done. Inhibitory something is inhibiting the works of enzyme. So this one is the normal enzyme pathway. Okay, normal enzyme, competitive inhibitor, this is competitive inhibitor, non-competitive inhibitor. Enzyme follows Michaelis-Menten kinetics. Okay, at low substrate concentration, reaction velocity increases linearly with substrate concentration. Okay, as substrate concentration increases further, the enzyme becomes saturated and the rate approaches a maximum velocity Vmax. Key parameters: Km, substrate concentration at half Vmax, indicates enzyme affinity. Km indicates enzyme affinity. Vmax, maximum reaction velocity. This behavior reflects the formation of enzyme substrate complex and is fundamental to understanding the enzyme efficiency and regulation. Regulation of enzyme activity. So we are seeing different types of how this enzyme activity is regulated. So it is either inhibited or activated, right? So what does normally occur? There's an enzyme, there's a substrate comes in and a product goes out, right? As soon as we put an inhibitor, the active site changes. This site is called active site. So this changes its site. Okay, formation is changed, conformation is changed. So when the substrate comes here to bind, it is not able to bind, so it just goes away. This is enzyme inhibition. Next, in activation, the substrate is there, enzyme is there, but they are not able to bind with each other because there is a difference in their conformations, right? But as soon as activator is binded to the enzyme, the conformation changes and the substrate is now able to get attached to the enzyme and a product is formed. Enzyme activity is highly regulated, allowing cells to control metabolic pathways efficiently. There are different types of regulations. Okay, so allosteric regulation, effector molecules bind at sites other than the active sites, altering activity. Covalent modification, example is phosphorylation and dephosphorylation. Proteotic activation, activate inactive precursors, zymogens become active enzymes. Feedback inhibition, end products inhibit earlier steps in metabolic pathways. These enzymes mechanisms ensure metabolic homeostasis, prevent unnecessary energy expenditure. So this was allosteric regulation, inhibition and activation. Effector molecules bind at sites other than the active site, altering the activity. So effector molecule binds at a site other than the active site and alters the altering activity. So activity is altered. Covalent modification we are seeing in phosphorylation and dephosphorylation. In proteotic activation, inactive precursors, zymogens, become active. Inactive becomes active. In feedback inhibition, end products inhibit earlier steps in metabolic pathway. Okay. Next is dependence of environmental conditions. So temperature is seen and rate of reaction is seen. At this temperature between 40 and 50, the rate of reaction is at its highest, and then the denaturation starts. Percentage active enzyme. So, and we see at this point only the enzyme is most active, or the rate of reaction is maximum. Enzymes are sensitive to environmental conditions, that is pH and temperature. Each enzyme has optimal pH and optimal temperature at its function most efficiently. Temperature, increasing temperature rises reaction rate up to a point beyond which enzyme denaturation occurs due to disruption of protein structure. Why does the denaturation occurs? Because of denaturation of protein structures. pH changes. pH changes in pH affect ionization state of amino acid residues, especially at active site, altering enzyme activity. Okay, so what does pH do? It changes in pH affects the ionization state of amino acid residues, especially at the active sites, altering the enzyme activity. Next is requirements of cofactors and coenzymes. So apoenzymes plus cofactors forms hollow enzymes, an active enzyme. So apoenzymes, protein portion, it is the protein portion or inactive form. So many enzymes require non-protein components. Okay, let us just remember things. There is a factor, cofactor, and there is apoenzyme, and they both make hollow enzyme. And there's a different part, that is a cofactor. Sorry. Cofactor. There's a different part, coenzyme. Okay, apoenzyme, coenzyme, and cofactor, and we have holoenzyme. So we are seeing cofactor plus apoenzyme, cofactor plus apoenzyme, they make a holoenzyme. Okay, apoenzyme is a protein portion and cofactor is a non-protein portion. They both are inactive. Okay, but the holoenzyme that is formed is active. Many enzymes require non-protein components. Apoenzyme is proteinaceous, cofactor is non-proteinaceous. Both are inactive. Holoenzyme is a mixture of both and it is active. Many enzymes require non-protein components for activity. Cofactors, inorganic ions. Cofactors are inorganic ions like Mg2 plus, zinc 2 plus. Coenzymes are organic molecules. Coenzymes are organic molecules. Cofactors are inorganic molecules. Prosthetic groups are tightly bound cofactors. Protein part alone, apoenzyme, is inactive. Complete activity is called holoenzyme. Active. Reversibility and direction of reactions. Enzymes catalyze both forward and reverse reaction depending on the substrate and the product concentration. Enzymes do not dictate reaction direction, rather thermodynamics determines it. Who determines the direction? The delta G. However, enzymes can strongly influence the rate at which equilibrium is reached. Okay. Next is sensitivity to inhibitors. Enzymes can be inhibited by molecules that reduce their activity. Enzymes can be inhibited by molecules that reduce their activity. Inhibition का मतलब यही होता है. Competitive inhibitors, there are different types of inhibitors. Competitive, non-competitive, uncompetitive, irreversible inhibitors. So weird. Competitive competes with substrate. Non-competitive inhibitors binds elsewhere and alter the enzyme function. Very nice. So competitive inhibitor, they binds with the substrate. Non-competitive binds with the enzyme elsewhere, but the enzyme which alters the active site, which alters the function. Uncompetitive inhibitors binds only to ES complex. Whatever ES complex is made, they bind to this, and maybe they do not allow the formation of product or separation of enzyme later on. Next is irreversible inhibitors. Permanently inactivates the enzyme. This comes to the enzyme and enzyme is dead. Irreversible. This property is crucial in pharmacology and toxicology. I have a subject named as pharmacognosy. And for first 3 months I was not able to say this word because I was so familiar with this word, and now I'm not able to say this word because this word is in my mouth every time. Next, enzyme as proteins. Some enzymes are proteins. Most of the enzymes are proteins. Only mostly known RNA that is enzyme, it is RNAs. We learned about RNAs also. So enzyme as proteins, structure function relationship. Many enzymes are globular proteins. So there are 4 types of proteins, right, according to its structure: primary, secondary, quaternary, and globular. So most enzymes are globular proteins and their activity depends on the 3-dimensional structure. The active site is formed by specific amino acid residue, create unique microenvironment. So how is the active site formed here? My globular Okay, I know it is not like this, but just for the sake of it, there are specific amino acid residues. Specific amino acid residues. Okay, they create a unique microenvironment. So when we see this, there's a unique microenvironment here. These are specific amino acids. So they form the active site or binding site of enzymes. Even slight change in structure, mutation, denaturation can drastically affect enzyme activity, highlighting the tight relationship between structure and function. Classification of enzyme. The classification of enzyme. There are different types of enzyme. It was classified with the help of IUPMB system. What is this system? What is the full form of this IUPMB? International Union of Biochemistry and Molecular Biology. International Union of Biochemistry and Molecular Biology. I really wanted to do masters in biochemistry, but well, I was not good enough for them. So now I am doing masters in a broader stem of biology, so that I can, if I'm not a master of only biochemistry, I can be a master of anything. Ha 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 ha. Enzymes are classified according to the types of chemical reactions they catalyze. So there are different type of chemical reaction we have been studying since senior years, like displacement, double displacement, and many others, hydrolysis, right, and redox reactions where only electrons and protons exchange themselves, right? And then if we are seeing the organic chemistry portion, we see groups go from one carbon atom to a different carbon atom, so that is a change in group, right? Like from one like glucose 1 phosphate, we are making glucose 6 phosphate. So the phosphate atom from carbon 1 is going to carbon 6. Who is doing that? How is these are all different reactions. So according to different reaction, there are different types of enzymes. These are standardized by International Union of Biochemistry and Molecular Biology. International Union of Biochemistry and Molecular Biology. This system is known as Enzyme Commission Classification, EC classification, Enzyme Commission classification. Each enzyme is assigned a unique 4-part EC number, EC 1, 2, 3, 4, which systematically describes its catalytic activity. EC 1, 2, 3, 4. First describes the main class, or the type of reaction we are dealing with. Second specifies the subgroup, group acted upon, or type of bond. What the type of bond is, this or this, this or this or something else, or what the group acted upon is. Next is third indicates subclass, more specific reaction details we are seeing. Next, fourth identifies this specific enzyme, what specific enzyme is within that category. For example, alcohol dehydrogenase is EC1111. It indicates that it is an oxidoreductase acting on CHOH group with NAD plus NADP plus as acceptors. Okay.
Yeah.
This classification is purely functional, which means it does not depend on enzyme structure, origin, sequence, but strictly on chemical reaction chemistry, which is universally acceptable. So we are not just seeing this is not upon how this structure of enzyme is, but how it is acting upon a reaction. Okay, we are always focused on the applications, what it can do for us, and not how it is doing. Not mostly, we are scientists, so we are seeing how it is doing, but we are always focused on what it can do for us. The classification is purely fictional, meaning it does not. Okay, next, so we are seeing the number ones. EC1, oxidoreductase. Let us just see, there are 7 different kinds of them: oxidoreductase, transferases, hydrolases, lyases, isomerases, ligases, and translocases. Okay, so O, T, transferases, hydrolases, lyases, isomerases, ligases, and translocases. 1 2 3 4 5 6 7. OTH, LILT, athlete. Athlete. Oxidoreductase, EC1, is the oxidation reduction or redox reaction we are seeing, which involves the transfer of electrons, hydrogen atoms, or oxygen atom between molecules. In biochemical system, oxidation typically refers to loss of electrons or hydrogen, whereas reduction refers to gain of hydrogen. Whenever oxidation is occurring, we see there is a loss of electron or hydrogen. Reduction is happening, we see gain of electrons or hydrogen. This is such a controversial statement, because what I am seeing is very false. Like, it's either electron or hydrogen. Why is a negative and a positive going and doing the same thing? This is a very wrong thing. So we'll Google the right thing. What is oxidation and what is reduction? What is oxidation and what is reduction? Oxidation, loss of electrons, as that means, loss of electrons is removal of hydrogen, and reduction is gain of electrons, that means removal of oxygen and gain of hydrogen. Wow. Let us see the structure. Loss of electron is gain of hydrogen or gain of hydrogen. Okay, so this is oxidation. Loss of electron is making it have or getting a hydrogen. Gain of electrons, I don't understand. Wait. Loss of electrons, removal of hydrogen. This is loss of electrons. Increase in oxidation number, decrease in oxidation number. Wow, I'm so confused right now. Let us see a different example. Zinc, okay, and oxidation number is increasing, ZnSO4. Okay, so now when they separate ZnSO4, we'll get Zn2 plus and SO4 2 minus, and CuSO4 goes from Cu2 plus and SO4 2 minus to Cu0. We'll see the electronic concept to ZnSO4, loss of 2 electrons, it is losing 2 electrons. Okay, so when it is losing 2 electrons, oxidation is happening. When it is gaining 2 electrons, reduction is happening. There was a time I was expert in this. Now I've forgotten everything. Oh God. Oxidation is loss of electrons. Reduction is gain of electrons. Okay. Oil rig. Wow. Oxidation is loss. Reduction is gain of electrons. Okay, sir. Anyways, let's move. Oxidation is loss of electrons, reduction is gain of electrons. I am not going for hydrogen, it is making me confused. Next, these enzymes require coenzyme such as NAD plus, NADP plus, FAD. So these are coenzymes. Enzymes have coenzymes that we saw. Enzyme, this total thing is an enzyme and it has a coenzyme. So the coenzyme are NADP, NAD plus, NADP plus, FAD, which act as electron carriers based on the mode of action oxidoreductase include. So mode of action is dehydrogenation, removal of hydrogen molecules, dehydrogenation. Hydrogen is removed. Oxidases, transfer of electrons directly to oxygen. Reductases, which catalyzes the reduction reaction. Mechanically, as emphasized in vote and vote, these enzymes stabilizes transition states, involve electron redistribution, and often tightly bound cofactors and prosthetic groups. These are central and metabolic pathways such as glycolysis and DC cycle and oxidative phosphorylation. Second is transferases. So the transferases catalyzes transfer of functional group from donor molecule to acceptor molecule. Transfer molecule may include methyl, acyl, glycosyl, phosphoryl and amino groups. A key group is kinases. This transfer phosphate group from ATP to substrate, a process fundamental to cellular signaling and metabolism. Aminotransferases, transaminases, transfer of amino group between amino acid and keto acid, playing a critical role in amino. So what are kinases? Transfer of phosphate groups from ATP to substrates. Okay. Second is aminotransferases. We are doing transfer of amino groups from amino acids to keto acids. Okay. Kinases, transfer of phosphate groups from ATP to other substrates. And aminotransferases, transfer of amino groups between amino acids and keto acids. Catalytic mechanism often involves formation of transient amine enzyme group intermediate or direct group transfers, but transfer facilitated by cofactors such as pyridoxal phosphate. These enzymes are highly specific not only for group transfer but also for both donor and acceptor molecules. So what is happening here? The catalytic mechanism, it is of this often involve formation of transient enzyme group intermediate, okay, or direct group transfer facilitated by cofactors such as PLP, pyridoxal phosphate. These enzymes are highly specific not only for group transfer but also for donor acceptor molecules. Next is hydrolysis. Hydrolysis catalyzes hydrolytic cleavage of chemical bonds using water. They catalyze hydrolytic cleavage of chemical bonds. This class includes enzymes that break peptide, ester, glycosidic and phosphoester bond. Include proteases which hydrolyze peptide bonds, lyases which break down triglycerides, nucleases which cleave nucleic acid. I'm tired, wait a second. So where were we? At hydrolysis, I believe. But before that, we should once again go back to this catalytic mechanism. So they are saying that catalytic mechanism involves the formation of transient enzyme and group intermediate. Okay, so whatever the group was, let us say A, it was attached to the substrate, but it during the catalytic mechanism it makes an enzyme and group intermediate, okay, or the direct group transfer facilitated by cofactors. It's either this or the group is directly transferred from substrate to product with the help of cofactor called PLP, which is also known as pyridoxal phosphate. These enzymes are highly specific not only for group transfer but also for both donor and acceptor molecules. Next is hydrolysis, EC3. What is E? Election. I forgot. Enzyme commission. I was like electro. Shut up, Apu. Okay. And hydrolysis, EC3. They catalyze hydrolytic cleavage in chemical bonds using water. This class includes enzyme that breaks peptide, ester, glycosidic and phosphodiester bonds. Okay, these enzymes break quite a quantity of bonds: peptides, ester bonds, glycosidic bonds, phosphodiester bonds. So examples are for proteases. Proteases break down the peptide bonds. Lipases, they break down the triglyceride bonds, and nucleases, they cleave the nucleic acid. Mechanically, hydrolysis often involve the nucleophilic attack. Hydrolysis involve the nucleophilic attack on the substrate, sometimes forming the covalent enzyme substrate intermediate, where it's described in serine as chymotrypsin. Wow. Chymotrypsin is a hydrolysis. Wow. So what happens that hydrolysis do a nucleophilic attack on substrate, okay, and then now they are forming a covalent enzyme substrate intermediate. So okay, these in serine, as described in serine proteases like chymotrypsin, as described in serine proteases like chymotrypsin, this active site frequently contains catalytic residues. Example: serine, histamine, aspartate, arranged in catalytic triad. These enzymes are essentially in digestion, intracellular degradation, nucleic acid metabolism. Next is ligases, EC4. Liases, what does liases do? They catalyze the non-hydrolytic removal or addition of group. So we have hydrolytic, now we have non-hydrolytic. First we had oxidation reductase, so loss or gain of electrons we are seeing there. Next is transferases, we are transferring a whole functional group. Next is hydrolysis, we are seeing the cleavage, we catalyze the hydrolytic cleavage of chemical bonds. Like if this is hydrolytic, we are using water. Now next is lyases, we are seeing that lyases catalyzes the non-hydrolytic removal or addition of groups to substrate, often resulting in the formation or breaking of double bonds. Using hydrolysis, they do not use water, and like ligases, they do not require ATP. Typical reaction includes removal of carbon dioxide, removal of water, cleavage of CC, bonds. For example, aldolysis in glycolysis cleaves fructose 1,6-bisphosphate into true phosphate 2-triose phosphate. Mechanistically, lyases often stabilize carbanion intermediates and use cofactors such as thymine pyrophosphate TPP. Wow. So we are seeing a difference here. No water is used, no ATP is used. We are removing carbon dioxide, decarboxylases. We are removing water, H2O, dehydratases. We are cleaving CN bonds, CN bonds. Okay, example is like fructose 1,6-bisphosphate is cleaved to 2-triose phosphate. Okay, and lyses are stabilized by carbanion intermediates or use cofactors such as thymine pyrophosphate. Next is isomerases. Isomerases catalyze intermolecular arrangement, converts some molecules into one of its isomers. These reactions involve structural reorganization without adding or removing atom. So this chemical formula, chemical structure, there is no change, no addition or no removal of atom is seen. Just a little bit of structural reorganization is seen. Okay, so subtypes, this includes racemases and epimerases, which interconvert stereoisomers, mutations which shift functional groups within a molecule. So okay, if you will be asking, here is also functional group and here is also functional group. Okay, but in this, the functional group is coming from another molecule, and in this, the functional group is from within a molecule. Cis-trans isomerases, we all know cis-trans, right? This is cis, this is trans. Okay, this interconversion is seen in isomerases. A classical example is phosphoglucose isomerases, which converts glucose 6-phosphate to fructose 6-phosphate in glycolysis. This enzyme is often operated through acid-base catalysis and transient intermediate formation. Next is ligases, EC6. Ligases catalyze the joining of two molecules within this simultaneous hydrolysis of ATP or similar nucleotides. Because of this enzyme requirement, there are sometimes called synthetase. They form bonds such as CCCOCNCS. We see cleavages occurring by lyases, but the formation of these bonds are occurring by ligases. Ligases catalyze the joining of two molecules, simultaneously hydrolysis of ATP. Okay. A key example, DNA ligase, which joins DNA fragments during the replication and repair. Mechanistically, ligases form activated intermediates, often involving AMP attachment to one substrate before bond formation. Each enzymes are crucial for biosynthesis and macromolecular assembly. Last but not the least, translocases, EC7. Translocases is a relatively recent addition by the International Union Biochemistry and Molecular Biology. Catalyzes the movement of ions or molecules across the membrane or the separation within the membrane. So we are seeing movement of ions across the membrane, or their separation within the membrane, or across the membrane. This is what we are seeing in this. Translocases, they are essential for establishing ion gradient, transporting metabolites, driving ATP synthesis or proton gradients in mitochondria. Example include ATP driven pump like Na plus K plus ATPase and ABC transporters. These enzymes could couple transport to energy sources such as ATP hydrolysis and chemical gradients. Next, we'll briefly now see these mechanisms that we have been discussing. Catalytic mechanisms. Catalysis is a process that increases the rate at which reaction approaches equilibrium. Catalysis, the workings of a catalyst. What does a catalyst do? It increases the rate of reaction approaching equilibrium. Okay, so catalysis is a process that increases at the rate at which a reaction approaches equilibrium. The rate of reaction is a function of its free energy of activation. A catalyst activates by lowering the height of its kinetic barrier, that is, a catalyst stabilizes the transition state with respect to the uncatalyzed reaction. There is, in most cases, nothing unique about enzymatic mechanisms of catalysis in comparison to non-enzymatic mechanisms. What apparently makes enzymes such powerful catalysts are two related properties: their specificity of substrate binding combined with their optimal arrangement of catalytic groups. Types of catalytic mechanisms we are now seeing. So acid-base catalysis, covalent catalysis, metal ion catalysis, electrostatic catalysis, proximity and orientation effects, preferential binding of transition state complex. So we have been reading multiple times about acid-base catalysis. So acid-base catalysis, or also known as general acid catalysis, is a process in which partial proton transfer from a bronzed acid, a species that can donate proton, lowers the free energy of reaction's transition state. Okay, from a bronzed acid, the H ion is transferred. Proton is transferred from bronzed acid, and this lowers the free energy of the reaction's transition state. For example, an uncatalyzed keto-enol tautomerization reaction occurs quite slowly at the rate of the high energy of its carbon ion-like transition state. Proton donation to the oxygen atom, however, reduces the carbon ion characters in the transition state by catalyzing the reaction. Reaction may also be stimulated by general base catalysis if its rate is increased by a partial proton abstraction by bronzed base, a species that can combine with a proton. Some reactions may be simultaneously subjected to both processes. Concentrated general acid base catalysis. So here we are seeing we have CH3COR and CHA. We have made a transition state, and from this transition state this H is removed. Now that's what we were seeing. From the bronzed acid, partial proton transfer is occurring. Okay, now so this lowers the delta free energy of the transition state, because now the energy of transition state has been lowered. It will reach to the equilibrium faster. Okay, later on it is said, just like we can do this with bronzed acid, we can do same thing with the Bronsted base, but here the partial proton abstraction occurs. Okay, it combines with the proton. Here, see, proton is added to decrease the free energy of reaction transition state. When they both occur simultaneously, it is known as general acid-base catalyzed reaction. Next is covalent catalysis. Covalent catalysis involves rate acceleration through the transient formation of catalyst substrate covalent bond. The carboxylation of acetoacetate is covalent. Wait, covalent catalysis involves rate acceleration through the transient formation of catalyst substrate. We are seeing transient formation of catalyst and substrate. Okay, covalent bond, rate acceleration through transitions. Okay, transition, because transition state is a state, transient formation is occurring. Okay, we are seeing that there is an acceleration. Okay, and it is done by covalent bond. So covalent catalysis, decarboxylation of acetoacetate is chemically catalyzed by primary amines, is an example of such process. In the first stage of this reaction, the amine nucleophilically attacks the carbonyl group of the acetoacetate to form skiff base imine bond. The protonated nitrogen atom of the covalent intermediate then acts as an electron sink so as to reduce the otherwise high energy enolate characteristics of the transient state formation and decomposition of skiff base, blah blah blah. So we are seeing acetoacetate, CO2 is removed, enolate is formed, hydrogen proton is added, and acetate is formed. Here acetoacetate, RNH2 is added and OH ion is removed. So we have a skip space. Skip space remove the carbon dioxide from this, and then it removes adds a proton. From here we remove the NH2 that we added in the first step and add a OH hydroxide ion that we removed in the first step and form the acetone. This was what was happening when transient state was not made. As soon as transient state is made, the process is way simpler. Metal ion catalysis. Nearly 1/3 of all enzyme requires the presence of metal ion of catalytic activity. These are two classes of metal ions requiring enzyme. I am so tired. So there are two types, metalloenzymes and metal activated enzymes. Metalloenzymes, they are tightly bound to the metal ions and mostly transient metal ions. Metal activated loosely bind alkalides and alkaline, Na, K, Mg, Ca. Metalloenzymes Fe, Cu, Zn, Mn, O3, Co. Metal ion participates in catalytic blah blah blah. I'm not reading this. Okay, if you want to read this, just read it. I'm not reading this. I'm tired. So, mechanism of chymotrypsin. We'll do this after a break.